The second topic is a simple yet really powerful concept. Let's do an intro. You all know from your undergraduate control class, if you have a steady state error, then you can use integral control to remove the steady state error in a PID, right? So okay, so, and you also know if you have integral control and you have constant disturbance, if you have constant disturbance, then it is also fine because of the integration action. So from undergraduate control class, you probably will derive the transfer function from the disturbance to the output and see the integral control, how it's going to make the transfer function dynamics change. Now let's try to look at the picture in this way. A PID control looks like this. It has a structure of Kp, Ki, and then Kd. And then if we have a constant disturbance, what is the Laplace transform of a constant disturbance? Right? A constant signal Laplace transform is 1 over s. And if it has a gain, then it's going to be d times 1 over s. So you see, actually, integral control and this constant disturbance Laplace transform, they share actually the same dynamics, core dynamics. Right? It is as if you intentionally create a disturbance model inside your controller, and somehow it's got canceled in the end. Right? So this gives some intuition of this internal model. Your controller has an internal model, internal copy of the disturbance dynamics in a way. That's the motivation here. Let's take a look at the details, though. So let's see an example of your plant is a first order system, right? It's a mass with a damping inside. Then let's say the PID control is the same as this. So let's take a look at the error signal. Let's say I have a disturbance rejection problem. I don't have any reference. All I want is to be able to control my plant so that the disturbance is not going to impact my output. So effectively, that's saying at steady state, I want this to be 0. Effectively saying I want this error to be 0 at the steady state. So let's take a look at this steady state error. Okay? So the steady state error in the Laplace domain is negative of y of s. And then y of s, we can take a look at this path from here to here. We know, so this is an input, and then it goes through this dynamics and then generates the output. So y of s is going to be transfer function from d to y times the input Laplace transform. So this is just an undergraduate Laplace transform analysis. It's going to be negative GS 1 plus GS and then my PID control. Someone quick at calculation can work on it and perhaps give me the answer after I finish cleaning the whiteboard. So E of S equals, if you do the calculation, it's going to be, let's do it together. 1 plus MSB PID and then 1 over MS plus B D over S. It's going to equal to 1 and then D over S, or there's a negative sign, I think. Negative. And then it's going to be S. So this is the key step. S in this little integration is going to flip up to here. And then denominator is ms squared, bs, kps, ki, and then kds squared. All right. So you see this term flips up and then creates this cancellation with the disturbance dynamics. All right? And then here, this polynomial is the closed loop characteristic polynomial. So the first goal to design PID is to make the closed loop stable. So this can be designed to have stable roots. Okay? So that means your E of S, your error signal, has this Laplace domain property. It is a constant divided by some stable polynomials. All right? So think about examples such as, recall, if you have an exponential function which dies out eventually, e negative t, the Laplace transform of this is 1 over what? S plus 1, right? If you have a signal that dies out eventually, the Laplace domain of this signal must have stable roots, stable poles. All right? Same thing here. We created this error signal analysis, and we see it is d over a stable polynomial, right? So from this analysis, because of this cancellation, this e will converge to 0. Regardless of d, it can be 100, 1,000, 10,000. In the end, it's going to go to 0. So that's the beauty of this. This disturbance model gets designed into this controller model, then the cancellation will happen naturally in this feedback loop. This is the constant disturbance term. Now, let's quickly extend the concept with this theorem. The theorem says, give me a disturbance structure. I don't need to know all the parameters. But if you just tell me a little bit about it, then I will be able to help you design closed-loop controllers to reject it. So it says, this is, yeah. So conditions are BS and AS has no coprime, no common roots to start with, which is a very basic assumption. And closed loop is stable, designed to be stable. And then it says, let design AC this way to contain the denominator of the disturbance dynamics in this controller denominator. Okay, so absorb this, and then you can design something extra. But contain this inside, then the disturbance is asymptotically rejected. All right, so very simple concept, but extremely powerful tool. To show this, essentially apply the same technique again. See the cancellation happening. Okay? So that's the tool that we'll be using later on. That's for it today.